Okay, so for lesson six, your last lesson of the unit, you are going to be just solving equations using logarithms. Or just I'm going to show you some examples that you could do for just solving problems in general for this unit, okay, so that you could see in your homework. So just remember a model for exponential growth for your exponential equations is p to the n, which just means your amount after your n after a certain number of growth periods. P to the o is that initial amount. You have 1 plus your rate of growth, and then you have your n is your number of growth periods. So you should have seen this last year in grade 11. Okay, so let's just go through a couple examples using this formula. There are 5,000 yeast cells in a culture. The number of cells grows at a rate of 25% per day. The function that models the growth of yeast cells is ND equals N naught 1 plus R to the exponent D, where N is the number of yeast cells, D is days after the culture started, N naught is the initial population, and R is your growth rate. So it tells you exactly what all of those things represent anyways in your formula. How many cells will there be 1 week later? Okay, so you have to figure out what these are. So your initial population, what does our yeast cells start at? So we're starting at 5,000. Okay, our growth rate is 25% per day. Okay, but we can't ever have it as a percentage. You need to convert it to a decimal. To do that, hopefully you know that's just divide by 100, and then your number of days is given here. So it says 1 week later. So how many days is that? So 7, okay, is 1 week. Okay, so all you're going to do simply there is plug in that information into your formula. So you're going to plug in 5,000, 1 plus 0.25 to the exponent 7. And then you're going to get approximately 23,841. Just make sure here, though, you are doing 5,000 1.25 to the exponent 7, and then you're doing the exponent with the base first, because you won't get the correct answer if you don't do that first. So you should get approximately 4.76837182, and then times that by 5,000 is that answer, approximately 23,841.9, or you could round to 842. So they are actually a little off on rounding there too, because I kept all my decimals here. Okay, so just make sure that you know how to solve that in between step using those equations. Okay, another example. Another example here, according to the U.S. Census Bureau's World Population Clock, the number of people in the world in 1950 was 2.5 billion. The population has grown at a rate of approximately 1.7% per year then. Create an algebraic model to predict the population in the future. Okay, so you know that your initial population, because at 1950 it was 2.5 billion. And you know that we're growing each year by 1.7%. So take it and divide it by 100, so 0.017. Okay, then you're going to just plug that information into your algebraic model, and then you can also add in this 2.5, 1.017 to the n. You just have to remember, if you were to solve any questions with that, your answer you would have to write is billion, because you didn't write 2.5 billion in your equation. Okay, so just make sure if you were to answer questions on that, but all it's asking us to do is create an algebraic model there. Okay, another type of example you could be asked is like, there are 100 bacteria in a petri dish. The number of bacteria doubles out every hour. So you could be asked to represent it in a table of values as a graph or as an equation. So you know that if you have the table of values, it starts at 0, the time starts at 0, and then your number of bacteria starts at 100. And because it's saying it doubles, you're going to multiply by 2 each time. So 100 times 2 is 200, 200 times 2 is 4, and you keep going. So that's how you'd represent it in a table of values. You can then take that table of values and you can graph it. Okay, so pretty simple there. Just take those coordinate points and plug 0, 100, 1, 200, 2, 400, 3, 800, okay? Or to represent it as an equation, you would take n, because that's your number of bacteria, is equal to 100, which is your initial value, times 2, because that's your growth factor, right? You found your growth factor here of 2, and that comes from that doubling scenario, okay? And then you put the exponent t. So another way you can write that is in brackets, okay? So you can also have it like that. Up to you. And then a final example I'm just going to use for logarithms that you might need is this change of base formula. So for any positive numbers a, b, and c, b cannot equal 1 and c cannot equal 1. Okay, so we're going to evaluate log 3 of 6 and round our answer to 3 decimal places. So if you're looking at this is log, and then b, and then this is your a. Okay, so all you're going to do is take that log of 6, because that goes on top, divided by the log of 3, which is your b. Okay, and then you're just going to plug it in your calculator. You should get those numbers, and then your answer is 1.6 whatever, and it says to 3 decimal places, so approximately 1.631 would be your answer there. Okay, so you just need to remember your change of base formula for some questions. Okay, so that's all for this homework today. So you're going to do page 1 to 4, 7, and 8 for homework. Just let me know if you have any questions. Good luck.